we're going to look at how do we actually calculate a binomial probability. So we're going to look at a fairly simple example. In many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1 out of 6. If x equals the number of 6s in 4 rolls of a fair die, then x is binomial with n equals 4 and p equals 1/6. So we have a binomial situation where success is getting a 6 and failure is not getting a 6. We have a fixed number of we know that dice rolls are independent. We have a fixed number of trials where n equals 4, and we have the same probability of success for each roll of 1/6. So let's start out by looking at all the different possible outcomes of the number of 6s we could get in 4 rolls of a fair die. We could get 0 6s, we could get 1 6, we could get 2, we could get 3, or we could get 4 6s out of 4. So there's 5 different possibilities when seeing how many 6s out of 4 that we could get. So what is the probability that x equals 0? In other words, that we didn't get any 6s. In other words, what's the probability that all 4 rolls are not 6s? So if the probability of, so let's just call this S for success, and let's call this F for failure. So the probability of a success is 1/6. So the probability of a failure is 1 minus 1/6, or 5/6. So we could call this P, and this would be 1 minus P. So that would be the probability of not getting 6. So what's the probability that all 4 rolls are not 6s? So that would be the probability of not 6 and not 6 and not 6 and not 6. Now I'm not going to have you write this out each time, but this is just to remind you that when we have 4 independent events like this and we want to know that all 4 happen, this and this and this and this, we multiply their probabilities. So this is just 5 6 times 5 6 times 5 6 times 5 6, because this is the probability of getting 4 failures in a row. Okay, so in other words, 5 6 to the 4th. And I'm not going to go ahead and calculate that right now. I just want to show you a pattern that happens here. So what's the probability that x is equal to 1? Now initially your thought might be, okay, that's just 5 6 times 5 6 times 5 6. There's my 3 failures, and then I got 1 success. And that would be almost correct, but not quite, because there's actually more than one way to get 1 out of 4, because the order matters here. Think of this as 4 different color dice. So let's say this was a red die, a white die, a blue die, and a green die. So getting a 6 on the green die would not be the same as getting a 6 on the blue or the red or the white die. So we have to think about all the different ways to get 1 success out of 4. And so we could have failure, 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 success like this, or we could have failure, failure, success, failure, or failure, success, failure, failure, or success, failure, failure, failure. So if we thought about rolling this die 4 times, there's 4 different ways to get 1 out of 4 of the 6. So we have to think of this as 4 times 5 out of 6 to the 3rd times 1/6. So this is, we have to take into consideration the number of ways things happen. So let's look at the number of ways that we can get 2 out of 6. So this involves making kind of an organized list. So I could have 2 failures and 2 successes, or I could have a failure, success, failure, success, or I could have a failure, success, success, failure, or a success, failure, success, failure, or success, success, failure, failure, and I think I missed one. Yes, I didn't do the one where the success is first and then the 2 failures in the middle and then a success at the end. Okay, so there's actually 6 of these. There's 6 different ways to get 2 out of 6. And if you can verify that for yourself. So this would be then 6 times 5 6 squared times 1 6 squared. So 2 times 5, 5, 6 times 5, 6, 1, 6 times 1, 6, but there's 6 ways for it to happen. Now, how many ways are there to get 3 out of 4 successes? Well, it'd be the same number as getting 3 out of 4 failures. And so we could have success, 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 failure. Then we could have this, I'm going to not say it because I'll just get my words tangled up saying it over and over. But we could have the same kind of situation as we did here. So we're going to have 4 times, in this case now, it would be 5 6 to the first, and then 1 6 to the third, because we're having 3 successes and 2 failures. And then the last one, how many ways to get all 4 of them 6s, would just be 1 6 to the fourth. So how does this lead us then to the binomial formula? On your formula sheet, it says this: if x has a binomial distribution with parameters n and p. In other words, n and p, the number of trials and the probability of success, are the 2 numbers that define a binomial distribution. Just like mu and sigma define a normal distribution. These are the parameters. So you have to always note what the parameters are for a binomial model. The formula looks like this. The probability that x equals k is equal to n select k, p to the, actually there's no parentheses around this on the formula sheet, p to the k, 1 minus p to the n minus k. So I want you to notice k here is the number of successes. Okay. N, of course, is the number of trials. So this is telling me, so right here is, this number here is the number of ways to get k out of n. So in other words, the number of ways to get k successes out of n trials. Here we have p is the probability of success, and then 1 minus p, of course, then would be the probability of failure. So obviously I'm raising p to the k power because that's how many successes I'm going to have, and I'm multiplying it times itself, k times. Then I'd be multiplying the probability of failure times itself, whatever is left over from n minus k. Now, just to remind you that n select k is a mathematical operation. It can also be written like this, nck. You might have seen it as n select r, ncr. So on your calculator, it's written as ncr. They use r instead of k. But it means this, n factorial over k factorial n minus k factorial. So let's look how this would play out with one of our examples up here. So the number 6 here. In this situation, n is 4 and k is 2 because I wanted to get 2 successes out of 4. So I would have 4 factorial, so this would be 4 select 2 in the binomial formula, 4 select 2. And this would be 4 factorial over 2 factorial, and then n minus k is also 2, and it would look like that. And if you recall, factorials, 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. This ends up being 24 over 4, which is 6. So that's where this number comes from, this 6 right here. This would be 4 select 3. This would be, the number 1 would be 4 select 4, because there's only one way to get 4 out of 4. This would be 4 select 1, and this would also be a 1 here. This would be 4 select 0. So this is known as the binomial coefficient. This tells you the number of ways to get the that many successes out of 4 trials. Now, you'll learn that we're not going to be calculating this by hand, but it's just good to know where the number comes from and what that means. So let's just do a few using the formula, and then I'll show you how to do some things with the calculator. So I've got kind of a silly example here. 8 totally unrelated people are stuck in an elevator when the power goes off. To amuse themselves, they talk about things like, how many of you can roll your tongues? Someone mentions that 70% of people can roll their tongues. If x is equal to the number of people on the elevator who can roll their tongue, what is the probability distribution of x? So is this a binomial situation? So let's look at this. B. So success, we'll just call that S, is you can roll your tongue. And failure is not roll. You can't roll. And let's see, do we have a fixed number? I is independent. Well, these people are totally unrelated, so we're going to say independence is okay here. They should be independent. And there's 8 people, so we have a fixed number of trials. We're saying out of 8 people. And the probability of success is P is equal to 0.7 for each person. So it shouldn't change based on, like, some people have one different probability of others. So just in general, people in general, 70% of them can roll their tongue. So that's the same for anybody that we would pick randomly. So we would say that the distribution here is binomial with n equals 8 and p equals 0.7. So this is how we identify the probability distribution. You have to give it its name and its parameters. Name and parameters. Just like you have to identify a normal model by its name and parameters, using the n and the parentheses. So there is actually a way to do that with binomial with kind of a shortcut, and I'll show you that in a little while. Next video, actually. Okay, how likely is it that exactly 6 of the people on the elevator can roll their tongues? So now we're going to say probability that x equals 6, and we're going to fill in our formula. So n is 8, so 8 selects 6, and then the probability of success is 0.7, so 0.7 to the 6, because I'm going to have 6 people that can roll their tongues, and then 1 minus p would be 0.3, and I think I'm going to put this in parentheses just to make it a little easier to see, and that would be 2, because I have 6 successes, then I'm going to have 2 failures, so probability of success 0.7, probability of failure 0.3. So on the calculator, we can do this as 8 selects 6. You can do n CR 8, 6 on your calculator times 0.7 to the 6 times 0.3 squared. And then I'm going to show you another way to do it, but let's just do it that way. You can literally type in NCR. This is also found in the probability menu, but it's just easiest to do this, I think. So 8, 6. And just to show you what that number is, that's telling you there's 28 different ways to get 6 out of 8. So I could do that using factorials as well. Yeah, just for the heck of it, we'll do that. So we can say 8 factorial, the factorial button's down here, divided by 6 factorial times 2 factorial. Okay, same number. Okay, that's where that comes from. So we have 28 times 0.7 to the 6th times 0.3 squared. So that's the probability, about a 29–30% probability that exactly 6 people in the elevator could roll their tongues. Where did I write that down? I don't think I wrote it down. So 0.296, something like that. Okay. How likely is it that more than 6 people on the elevator can roll their tongues? So the probability that x is greater than 6. Now I want you to note that this is a discrete random variable. So in other words, it can't take on the value 6.5 or 6.1 or 6.3 or anything like that. It has to be 6 or 7 or 8. So when I say the probability of x greater than 6, that means the probability that x equals 7 or 8. Or you could say the probability that x is greater than or equal to 7. So I want you to notice that greater than 6 and greater than or equal to 7 is the same for a discrete distribution. So that would be 8 select 7, 0.7 to the 7, times 0.3 to the first, plus 8 select 8, 0.7 to the 8, 0.3 to the 0. Well, the number of ways you can get 7 out of 8 is 8 ways, just like 3 out of 4 is 4 ways. So 8 times 0.7 to the 7th times 0.3 plus 8 out of 8, that's just one way. So this is, and 0.3 to the 0 is 1, so this is just 0.7 to the 8th. So I could also calculate that, so I'll take a second and go calculate that. And then we'll look at an easier way to do this. I just wanted to get you familiar with the formula. So let's go ahead and do this. So doing this on the calculator, notice this is this or this, so you add in between. And it was about a 26% probability that more than 6 people on the elevator can roll their tongues. In the next video, then, we're going to look at where did this binomial function show up on your calculator, and how do you do this in a more efficient way on the calculator.